and why the system was created, so that system should fulfill its objective, so its intended purpose. If it fulfills its intended purpose, we can say that the system is reliable. But obviously there has to be some metrics that will give us whether a system is highly reliable, moderately reliable, or less than required level of reliability. But we need to know that, okay? So reliability is also a measure of the ability of the system to perform its intended function. The same thing, So reliability measures the ability of a system to perform its intended function. So I'm using this laptop to present my slides today. So if this laptop stops working, right now, this whole exercise will be interrupted. So I will deem this laptop or this device as unreliable in that case. So high degree of reliability means there should be very less number of failures, lesser chances of failures. Low degree of reliability means there will be higher chances or higher number of failures. So reliability is associated, or reliability can be evaluated not only for electrical power system, but it can be performed, it can be evaluated, or it can be extended for evaluation of any type of engineering systems, be it in the field of electronics, be it in the field of process engineering, be it in the field of civil engineering, aerospace engineering, everywhere. So reliability assessment is very critical. So we need to know whether a system is reliable or not. But to know that whether the system is reliable or not, we need to carry out a reliability assessment. So we need to carry out reliability assessment. So reliability assessment in most of the cases are carried out in two approaches, two methods. One is deterministic, another is probabilistic. As the name itself suggests, a deterministic approach mostly is intended to determine the level of reliability. But similarly, it is to fix if there is certain level of reliability required. So what level of reliability required? Or to resolve any issues related with the reliability or unreliability of a system. Or if you are a regulator, to regulate means to force or to enforce a regulation that this much reliability is required. For example, if it is a power system, then the reliability may be, you must have this much of percentage reserve margin in the system. That is one of the regulation. Or you can also limit the minimum level of reliability that a system can have. So lesser than that is not permissible. Or simply you will define what is required for a particular system. So deterministic reliability is mostly carried out or enforced in three different ways. One is the percentage reserve. This is related with the power system. One is the percentage reserve margin. That is, if a power system is operating, then the level of reserve required in case of generation capacity can be certain percentage of the total load in the system or the peak load of the system. If the system is having a peak load of, let's say, 100 megawatt, then if we enforce a percentage reserve margin or percentage reserve margin as the reliability criteria, then it can be either 10%, 12%, 15%, 20%, any percentage margin you have assumed or you have considered for that particular system. So usually that percentage reserve margin lies somewhere between 8% to 20-25%, depending upon the size of the system. For a very large system like that of Indian power system, the reliability margin required in terms of percentage reserve margin will be in the lower side, that is around 8 to 10%. But while for a small system like that of Nepal, where total system demand is around 1,002 to 1,300 megawatt only, the percentages or margin may be on the higher side, that is 20% or even 25%. So one of the method is percentage reserve margin. Another is to fulfill n-1 criteria. That means if one of the generating unit fails, the system should continue to supply the demand imposed on the system. Means one unit may be any unit, but the worst impact on the system will be if the largest unit fails. So sometimes it is also called loss of largest unit, LOLU. So if a system is having a very large unit and if that unit fails during the peak load condition, then there might be scarcity or deficit of power. So n-1 criteria should be fulfilled, or that can be one of the deterministic criteria in the power system. And another is a worst case condition. So that worst case condition may be, it can be n-2 also, or it can be some combination whereby system is subjected to severe deficit of power. So obviously that is not, we do not consider the natural calamities or effect of nature on the power system when we define or when we determine the reliability criteria, but worst case condition may be series of cascaded events that will create problem in the power system. So that is the deterministic criteria. So you already determine, okay, these criteria needs to be fulfilled in a given power system. So these are the deterministic criteria. Now let's move to the probabilistic approaches. Probability, the basic definition we all know. We have been going through this definition of probability from our high school days and the university and till now also. So it is a likelihood of an event, the expected relative frequency of occurrence of a specified event in a very large collection of possible outcomes. So if you have a very large number of possible outcomes, and among those large number of possible outcomes you are interested in a particular type of outcome, then you will find out. So you will find out the ratio, a particular type of outcomes divided by the large number of outcomes, all possible outcomes, that will give you the probability of that particular outcome occurring. So probability is a quantitative measure of the likelihood of an event. So it will give you, it will quantify, what is the likelihood of a particular event occurring. It is also a quantitative measure of the uncertainty associated with the event occurring. When we say probability, that means it is always associated with uncertainty. It may be, the probability value may be high, but still the event may not occur at all. So the uncertainty is always there. So probability may be very low, but the event may occur. Like you can win a lottery ticket. Your ticket can win a lottery. Means there is always a very low probability that a particular person wins, but one of the person will win the lottery. So there is a very high degree of uncertainty associated, and it is a quantitative indicator of uncertainty. So it will indicate how uncertain things can be. So probability concepts provide the ability to quantitatively incorporate uncertainty in the power system planning application. So because of this probability concept, we are able to quantitatively incorporate the uncertainties that exist in power system planning. So we have to incorporate. If it is deterministic criteria, it is very difficult to incorporate them quantitatively, So this cannot be done using deterministic method and criteria. So that is the advantage of using probabilistic approaches. Okay. Now, the reliability, in a system, it can be any system, you use or you try to make the system as reliable as possible, but you have to know whether by trying to make the system more reliable, you are investing too much in the system or not. Because sometimes you can see in this figure, in the start, you can see the reliability is increasing rather fast with the system cost. Means you are making investment and the reliability is increasing rather fast, at a quicker speed here. You can see this left-hand side. So, but towards the right-hand side or near the dotted line, which is the upper limit of the reliability, possible system reliability, we can see the increase in reliability is rather very, very slow. But the increase in system cost is still at the same pace, same rate, So that means how much further to invest in the system. We know that additional investment usually makes the system reliability higher, but whether that additional system investment is bringing enough reliability increment or not, that needs to be evaluated. So to do so, we need to be able to evaluate the system reliability. We need to be equipped with the methods and techniques that are used to evaluate the reliability of the system. So this incremental cost, delta C is the incremental additional cost made in the system, and delta R is the incremental reliability enhancement of the system. So we need to compare those two, because delta C is the additional cost that we are making into the system, and delta R is the additional reliability that we are getting from that incremental investment delta C. So delta C is the cost usually measured in terms of rupees or pound or dollar, where delta R is a reliability, it's a number only, it is a dimensionless. So how to compare, how to compare whether we are getting sufficient reliability enhancement or not by this incremental investment. So for that reason, we need to be able to assess the reliability worth. Means what does in terms of money that incremental reliability means. So what is this delta R? So we have to translate this delta R, or we have to be able to express this delta R in terms of monetary values. So how we will translate? For example, when we go to the shop, we will be having these Diwali days, and this is the shopping, time also for many households. So there are so many offers, and we go to a shop and we are interested in purchasing any household appliances like TV or like a washing machine or like a laptop, or these mixtures or micro oven, anything, or air conditioner. So you look at different brands and they have different prices, and they do have different, guarantee or warranty periods also. Those very reputed brands, they may provide you longer period of guarantee or warranty, but their cost may be high, their price may be high. Whereas less reputed brands may not give you that extended warranty or guarantee, but they will come cheaper. So you have to compare. So we can connect this with the reliability. Those reputed brands, they are known for producing quality products. Their products are more reliable. They are less prone to damages. So they are expensive. They are expensive. They are more costly. Whereas the lesser known brands, they are cheaper, but they are not that much reliable. At least we do have that type of perception. Maybe sometimes you purchase a lesser reliable product or not that much a high quality brand, but that product still works very well. You will find some of you will have found like that, yeah, but that is very rare. In most of the cases, those products which are reliable, which cost more, they are more reliable and they cost more. So reliability comes with cost. So highly reliable means you have to pay more for that. Okay. So when you make investment in making a product more reliable, means whether making the product more reliable is worth doing so or not. If the reliability benefit derived from further investment made in the system is comparable with the investment made, then you may continue to invest in the reliability enhancement. Or what we say is the worth or the benefit of reliability should be higher than the investment made to get that additional benefit. So if that is the case, we continue to make investment in the system reliability. Otherwise, we stop there, because when your investment is higher and your return or your benefit are lower, benefited. So there you have to stop. So that may be the stopping criteria for making any additional investment in the system to improve the reliability. So usually, mostly this curve is applicable not only for electric power system, but this has been derived for electrical power system, but this is applicable in any type of engineering creation, engineering system that we build. So what are these curves? In this left hand side, you can see this vertical axis. This is the cost in the left side, and in the right side, this dotted line, this is the reliability, the threshold reliability, so it's reliability of 100%, so, and you can see this line of a system cost. So what is a system cost? System cost means you try to make the system more reliable, you have to invest more. You invest less, your system is less reliable. You invest more, your system is more reliable. For example, in any product like those products manufactured by reputed multinationals like Samsung and LG, so they are making very high quality products. They have different range of products, and their products are good. Their prices are also high. So why their prices are high? Because their system cost or the investment cost is also high, and they invest not only in the production process, but they invest in research and development, they invest in quality control, they invest in training of their manpower, building human resources, retaining human resources. So they pay high salary to their workers. So their investment cost is high. So the system cost is high. System cost is high. Means they make more investment, so their product are more reliable. On the other hand, who should pay for the high degree of reliability? It is the customer, because whatever investment has been made by the system owner, the whole investment needs to be returned back or needs to be heard from the customers. If they fail to get that return back from the customer, then the system owner or that particular business entity will be in loss. So whatever investment is made in the system, that has to be returned back, or that has to be returned back from the customer. They have to get it returned from the customers, because when customer purchases certain product, they will pay for it. If the system itself is a high cost system, then their product will be also expensive. So customer will be paying more for their product. So this is this line. In the other hand, we have another cost called customer cost. You can see this almost exponentially decaying this curve. So this customer cost is nothing but cost incurred by the customer because of use of the product produced by this system owner, by this producer. So if the customer uses the product and the customer does not get what he wanted or what he intended to get from that product, then the customer cost will be higher. Means what type of customer cost? Customer cost means customer's inconvenience cost. Means if the product's reliability is low, the customer's inconvenience cost will be very high. If the product reliability is very high, then the customer's inconvenience cost will be very low. For example, if the product is of low quality, we purchase a television and the television, happened to be a low quality television. So the television was, purchased to watch certain popular serials, popular, movies or popular programs, news broadcast, etc., etc. But because it was of low quality, the customer did not get that intended benefit. That means the customer's inconvenience cost is high. But see, these customers' inconvenience cost may not always be possible to measure directly, because that inconvenience cost has to be measured in indirect manner. But there is an inconvenience cost, and you all will agree that the lesser the reliability of the product, the higher will be the inconvenience cost, and the higher the reliability of the product, the lesser will be the inconvenience cost. Because if the product quality is very high, then the inconvenience is very less. So if it is a low inconvenience, then the cost associated with the inconvenience will also be low. So we have to add both of those costs, system cost, they will be extracting back from the customer, and the customer interruption cost or customer cost, that is also borne by the customer. So both of these costs are borne by the customer. So when we add together, this will give the total customer cost, or also called total societal cost, total societal cost. So we can see this curve, this is like a, like a valley, and we have a minimum somewhere here, and this minimum represents the minimum total societal cost or minimum total customer cost. So this cost or this total minimum is what we intend to achieve for any type of engineering system. Any type of engineering system, we try to get this one. But sometimes if somebody is very much interested in having a very, very high quality product somewhere in this region, reliability almost in the 100% region, then he or she will be paying very high price for that, but that may not be the optimal reliability condition. But somebody is interested in purchasing those products, fine, they will purchase that. Okay. But if we consider an electric power system, then it's not like that, because from an electric power system, there cannot be variation, there cannot be different offerings from an electric power system. Like we can go to a shop, we can purchase different type of vehicular brands. We can purchase Maruti, we can purchase Kia Motors product, we can purchase Hyundai's product, we can go for, if you are going towards the higher end, then you can go towards this Honda or Toyota, or if you are interested in even higher brands or better brands like BMW or Mercedes, or if you are much interested in sport brands, you can go for Ferraris like that. But they all do have different cost, different cost. So their cost, they don't need to find this R optima, for them there is no R optima, because there are only limited number of customers. But here, in case of electricity supply system, we all get electricity supply from the same national grid or same electricity supply system. Where we are located, there is a distribution network available, so they will be supplying power to our household. So we all get electricity from the same system. So therefore, it is imperative for us to find out this R optima. That is for society, So therefore, it is called, this total cost curve is called societal cost. Means this is the system cost, or this is the investment made by the electric utility in bringing electricity to our household. So the more investment they make, the more reliable will be the power supply. Whereas this customer cost is cost incurred by the customers because of unreliability of the power supply system. If the supply system is not that much reliable, then our cost will be higher. So how our cost will be higher? You can get direct answer. For example, if I am a household consumer, then if the power supply reliability is very poor, I will be opting for alternate supply. Maybe I'll have a storage battery and inverter, or if there is such provision or such possibility to get supply from another alternative source, from maybe we have, if we are a large consumer, then I can have diesel generator also, which is a standby supply system. And the cost of operating a diesel generator is high, its fuel cost is high, and it requires additional investment to be made in the diesel generator. Similarly, additional investment has to be made in system that we have to put in place to get electricity when there is no supply from the grid available. So that means low reliability means this customer cost, or what we call this cost as a cost associated with unreliability of the power supply system. This cost is higher. This cost is higher. So we are operating in this region. So system investment is low. Why unreliability? Because there was low investment. Low investment in what? Low investment maybe in generation. We did not have sufficient generation facility. Low investment in transmission network. We did not have, sufficient transmission facilities to transmit power from generating station towards the load center. And also we may not have, good distribution network. Whether either it can be poorly managed, or repair and maintenance is carried out in a very poorly managed fashion, or we have many transformers that are already overloaded and many distribution lines that are already overloaded. So we did not make enough investment. So that's why this investment cost was low, or the system cost was low. Therefore, the reliability was poor. So because of the poor reliability, when system or investment cost is low, reliability will be poor, and the customer cost, because of poor reliability or unreliability, will be high. So when we add them together, total cost is also in the higher side. On the other hand, if we made more than required investment in the system, means we try to make our system as reliable as possible. So to improve the reliability, we kept on investing and investing and investing without knowing where is the optimal reliability level for the given system. So when making that investment, we got very high degree of reliability. But when you make huge investment in electricity supply system, to remain afloat, that system has to recover its investment. And from where it will recover? It will sorry. It will recover investment from its customer, from the sale of the electricity. So that means they have to increase the price of electricity. They have to increase the price of electricity. Who will pay for the higher price? Obviously, the customer will have to pay the higher price of electricity, because the price has been high. Customer will be paying more for the same electricity. The quality of the reliability of the supply is very high, but whether that reliability was necessary or not, how to know? That will be known only when we are able to know what is the unreliability cost. So when we add both of them together, we will find this type of total societal cost, where there will be some single minimum point, and that single minimum of the total societal cost or total cost to the customer represents the optimal reliability of the system. That is the optimal reliability of the system, this R optimal. But what happens, it's not that easy to find this R optimal. You cannot find it, analytically, you don't know, the system cost, you are making more investment, your reliability is increasing. This system cost. You have control over the system cost. But to know the unreliability cost, and this unreliability cost consists of certain components that are not directly measurable. They cannot be measured directly. So there is the difficulty in getting this customer cost. Okay. So therefore, many power systems worldwide, they find it very difficult to locate this optimal value of reliability, and they end up either operating at a reliability that is slightly higher than the optimal reliability, and in many cases they end up operating at a slightly lower than the optimal reliability level. So what happens in developed countries, in advanced economies, where customers of electricity are very, very conscious, and every aspect of life is associated with electricity. Without electricity, we cannot do anything. These days we are talking about electric vehicles, charging stations. So again, electricity. Earlier we are using gasoline. Now we are converting towards electricity, electric vehicle. So that means reliance on electricity is increasing day by day. So if there is no electricity, there might be huge uproar, there might be a riot if you do not have prolonged hour of without electricity, So therefore, the electric utilities there tend to operate in the region slightly right of the R optimal, slightly right of the R optimal. Whereas in developing countries, we may not be that much, um, customers' responses, we end up operating either in the slightly left side of the R optimal, or we are not bothered at all, and we do not have means and mechanism to find out what is the R optimal, and therefore we don't know whether we are operating in the optimal region or suboptimal region in the either left side or the right side of the optimal reliability. But see, if we have less reliability, then also the cost to society is high. If you have more than required reliability, then also cost to society is high. Usually, in developing countries, there is a scarcity of fund. So we do not, the government or the utilities, they may not have sufficient fund. So usually they end up in the left side of the optimal reliability region. Whereas in the developed countries, the case is not like that. And as I mentioned earlier, customers are very much concerned about availability or supply of electricity, and their lives are too much intertwined with electricity. Therefore, they tend to operate in the slightly right side of this optimal reliability level. So power system reliability assessment is usually divided into two areas of adequacy and security value. So we need to know, whether the reliability, we have sufficient reliability or not. So we need to evaluate reliability. We have to assess the reliability. So usually the power system reliability is divided into two areas. One is adequacy, another is security. Adequacy means whether we do have sufficient facilities required for the power system or not. So first and foremost is whether we do have sufficient generating facility in the system or not. Or in other words, whether we do have sufficient generation available in the system or not. For example, if the cumulative load is, let's say, 100,000 megawatt, what should be the adequate generation capacity required for the system? It's not the 100,000 megawatt only. It should be more than 100,000 megawatt. So how much more? 110,000 megawatt, or 1,500 megawatt, or 120,000 megawatt? That we need to decide. But it should be adequate as per our evaluation. Okay, and the security, this is the ability of the system to respond to disturbances arising within the system. Means there might be some type of disturbances. So after those disturbances, the system must be able to respond to those disturbances and remain in secure operation. Okay, remain in secure operation. So that type of disturbances should not be able to, lead towards, sustained scenario or sustained condition whereby system is unable to meet the imposed demand. Okay, so that is security. So security is it's a temporary phenomenon or transient phenomenon, related, whereas adequacy is a steady state phenomenon, So it's like a steady state analysis and like a transient analysis. And the performance of power system under extreme events such as earthquake, weather-related phenomenon, warfare, and terrorist activities are not considered in reliability assessment. So those external factors are not considered. If we consider those external factors for reliability assessment and to meet the currently the existing reliability metrics or reliability level, then the system will become very, very expensive. Okay, the system will be very, very expensive. And As you know, a power system is a hugely interconnected system. It is, or it may have, for example, for a small system like Nepal's, we have maybe only around 40 generating stations. Yeah. And some generating station will have 2 units, some generating station will have 7 units or 10 units. But in altogether, there might be no more than around 200 generating units in Nepal's power system. Whereas if we look at the Indian power system, it's one of the largest power systems in the world. Yeah, one of the largest power systems in the world. So there are thousands and thousands of generating units. There are hundreds of thousands of kilometers long, transmission lines. Means if we talk about the total length of the transmission line. Similarly, there are very large number of substations operating at different voltage levels, and there are again very large number of distribution networks. Those distribution networks are serving or working in urban areas, suburban areas, rural areas. The total cumulative length of those distribution lines may run into millions of kilometers and more, many hundred millions of kilometers, maybe. Yeah. So when reliability of a system is evaluated, or we try to evaluate the system reliability, it is rather easier for us to analyze these different, functional zones separately. Because generation, whether generation is located, maybe it may be located anywhere, but the purpose of the generation facility is to generate electricity. Similarly, transmission line or transmission facilities, again, wherever it be located, its main purpose is to provide a highway for transfer of bulk amount of power. It's like highway provides, facility for large vehicles to, fly through it uninterruptedly. Similarly, transmission line is capable of providing facility for transfer of huge amount of power, large amount of power, so transmission facility. And at the end, there is a distribution facility or distribution system. These distribution system or distribution facilities are utilized to distribute electricity or to get electricity to the ultimate consumers, households, industries, commercial complexes, and etc. and etc. Okay. So therefore, they are three different functional zones. So that's why they are, separately treated. But see, when we are interested about knowing whether sufficient generation facility exists in the system or not, it is better for us to consider only the generation facility. No need to know the transmission network and distribution network. Putting them together will make system more complex and the analysis more time consuming. But if our purpose is to know whether sufficient generation facility is available in the, then we should consider only the generation system, only the generation facility. So we can put together all the generation facility, without considering the interconnecting transmission lines. Although we know that these generation facilities are not at one place, but they are interconnected to each other via transmission line. But for the purpose of knowing whether we have sufficient generation in the system or not, we can put them together and carry out the analysis that is called hierarchical level 1 analysis or HL1 analysis. And now the power is generated and it has to be transmitted through transmission line. So generated power now has to be transmitted through the transmission line. So to know whether in a bulk load point, whether power is available or not, we need to know both about the generation facility and the transmission facility. So we put them together, both the generation facility and transmission facility, and analyze the system. You don't analyze the system by considering only the transmission facility, because only the transmission facility means it doesn't make any sense. You have to have some generation. So from where? From the generating system. So therefore, the generating stations or the generation facilities are now connected to the transmission facilities, and we assess whether or not at a particular point of interest electric power is available or not, or whether at a particular point with what probability electricity will be unavailable. To know that, we need to consider both the generation facility and the transmission facility. And this is called hierarchical level 2, which consists of both generation facility and the transmission facility. And then finally, we reach the distribution facility, because the power that is available at the end of the transmission system, that has to be transferred to the distribution facilities and then consumed by the consumers. If that power is not consumed, then for what purpose we do have that generation facility, transmission facility, and distribution facility? That electric power has to be consumed. So to know what is the reliability or what is the unreliability of electricity supply at a distribution feeder point, we need to know, or we need to consider the generation facilities, transmission facilities, and the distribution facility. So by analyzing all these facilities together, creating a system whereby we represent presence of generation facility, presence of transmission facility, and presence of distribution facility, we are able to analyze the reliability or unreliability of electricity supply system at a particular point in the distribution facility. So this is called hierarchical level 3. Okay. So if we are interested in knowing the reliability of power supply system at our household, we need to carry out this combined, HL3 level study, which consists of all the 3 facilities, 3 functional zones: generation, transmission, and distribution. However, because of the complexity that is present there, because in generation facility itself, there are very large number of generating units. And when it is added to the transmission facility, then when we add transmission facility, further large number of elements are added, because one transmission line is one element. So that means we are concerned with very large number of components. So therefore, usually what happens, to analyze the distribution system or distribution facility or hierarchical level 3 studies, we assume that at the end of the transmission network or the transmission facilities, power supply has a certain level of reliability or unreliability, and from that point onward, we will evaluate the distribution system's reliability or unreliability separately. So we do not consider all the 3 functional zones together, because that will make the system too much complicated. And the level of accuracy that we achieve by considering all the 3 functional zones together is comparable with the level of accuracy that is achieved by considering the distribution facilities separately, by considering that at the end of the transmission network from where distribution facility starts, a certain level of reliability obtained from HL2 analysis, and from there onward analyze the distribution facility only. So therefore, the degree of complexity in doing so will be tremendously reduced. Therefore, in distribution systems case, or HL3 analysis case, we only consider the distribution facilities and do not consider generation and transmission facilities together. Okay. And now let us move to basic concept in HL1 analysis. We have in HL1 analysis or HL1 evaluation, we are mostly concerned about whether we have sufficient generation capacity or not. So to do this analysis, we use, first of all, we need to find out what is the reliability or probability of a particular unit or particular event occurring or not. This is as per definition. Its limit n tends to infinity, f divided by n, where f is the frequency of occurrence of a particular outcome, n is the number of times experiment was repeated. So this definition will be used to find out the reliability or unreliability of the component also. Obviously, there will be slight variation, and we are interested about knowing availability of unavailability of the equipment. See, unavailability of any equipment or availability will be evaluated by this expression. Unavailability is sum of the total outage time divided by sum of total outage time plus sum of total operating time. This will give us unavailability of a particular component. Or similarly, availability, if I try to find out, this will be equal to sum of the total operating time divided by sum of total outage time plus sum of total operating time. This will give availability. So unavailability and availability are complementary. So availability is equals to 1 minus unavailability. Unavailability equals to 1 minus availability. And for generating unit, this unavailability is commonly referred as force outage rate. Force outage rate means the component in an outage because of the force outage, a random failure as we call it. Okay. So to know whether the HL1 analysis or HL1 analysis gives us required level of adequacy or not, we use a simple technique. We use a binomial distribution, and the binomial distribution where a particular component can reside in two states. So if it is a component, if it is a generator, then generator can reside either in operating condition or it can reside in failed condition. Okay. Or if it is an experiment, then the experiment can in success or in failure. Okay. So P represents probability of successful outcome, Q represents probability of failed outcome. So if it is for a generating unit, then we can say P is a generating unit is in working condition, Q is a generating unit is in failed condition. So for a binomial distribution, we can use these expressions. If it is a two-state system and if the number of experiments are 2, then it is P plus Q to the power 2, P square plus twice PQ plus Q square, where P square is in both the experiment the outcome will be successful. Twice PQ means there will be two outcomes such that one outcome will be successful and the other outcome will be failed. And Q square means in two experiments there is a probability that both the experiment will be failure only. So okay, so in this way we can carry out this expansion, and this is the expansion of binomial expression P plus Q to the power n. So this is n number of experiment, and by this, n minus 1, n minus r minus 1, p to the power n minus r, q r, this is divided by r factorial. This is the probability of exactly r failures and n minus r successes. Okay, n minus r successes in n number of trials. Okay, in n number of trials. This is represented as PR C R taken n number of experiment R taken at once, P to the power n minus R, Q to the power R. Okay, so the outcome of the binomial distribution can be used to find out a particular outcome. A particular outcome. If we are interested in knowing one unit available, one unit unavailable, then in two number of experiment, the second term will represent that. If we are interested in knowing both the units available, the first term will be useful for us, and so on. Okay. So generation capacity planning. So how do we plan generation capacity? For HL1 evaluation, the main objective is to assess the adequacy of generation facilities in the system to meet the existing or expected demand. Okay, existing or expected demand means if it is the existing system, then existing demand. If it is a new system, then it is expected demand. The simplest method of generation capacity planning is using binomial distribution. A generating unit in general can be represented by two state model: up state, operating, and down state, fail. Okay, two state model. In principle, a generating unit can remain in n number of states: up state, partial output state, down state, standby state, and so on. In partial output states, you can have multiple partial output state. So if it is a generator is rated for 100 megawatt, if it generates 95 megawatt, that is also partial output state. If it generates 90 megawatt, that is also partial output state. If it generates 10 megawatt, it is also partial output state. So there can be n number of possible states for any generating station in principle. But usually we are concerned about two-state model, whereby we represent a generating unit whether it is in up state or operating state with full capacity, or it is in down state or failed state with zero capacity. Okay. Now let us consider two 10 megawatt unit that can remain in two states, up and down, and the force outage rate is 0.02. Okay, force outage rate. Usually for generating units, the force outage rates are in the range of, it's from 0.05 to 0.01. If it is a very reliable generating unit, then its generating force outage rate will be lower. It can be 0.01. But if it is less reliable, then it can be 0.05, or in some cases it can be 0.1 also. That means 10% of the time we can expect the generating unit not to be in operational condition. So we can expect that. So binomial term for this two-state system, this is P squared, this P squared. So 2 units up, twice PQ, 1 unit up, and Q square, both unit down. This is Q squared, so it square got missing. So if 2 units are available, we have 20 megawatt available capacity. What is the probability? So 1 unit being available, the force outage rate is 0.02. So the availability is 1 minus force outage rate, that is 0.98. So both the unit being available at the same time means we have to multiply P with P. There are 2 units. So P squared, that is 0.9604. And cumulative probability means probability of finding, 20 megawatt or less. 20 megawatt or less is 1. because we can find 20 megawatt with this probability, and we can find 10 megawatt with this probability, and we can find 0 megawatt with this probability. So 20 megawatt or less is 1. So similarly, twice PQ, 1 unit of any one of the units can be of either unit A or unit B if we name those two units as A and B. So capacity will be 10 megawatt only, whether A is available, also 10 megawatt, whether B is available, also 10 megawatt. So probability is 0.0392. How do we find it? We multiply 2 PQ. P is the availability, 0.98. Q is the unavailability or force outage rate, 0.02. Twice PQ, you multiply it and you get 0.392. And now probability of getting 10 megawatt or less, 10 megawatt or less is this 0.392 plus 0.004. So cumulative probability is 0.396, or we can get this cumulative probability by simply subtracting from 1 from the above cumulative probability, this probability. 1 minus 0.9604. We'll get this probability. And similarly, when both the units are out, both are down, we have 0 megawatt available. What is the probability? 0.02 into 0.02. So it is 0.0004. Okay. And what is the cumulative probability? Again, I subtract from 0.0396 this probability, 0.0392. I get 0.004. This means probability of 0 megawatt or lower means nothing. It's 0 only. So probability of 0 megawatt being available is 0.004. It's the cumulative probability. Okay. And this is for a 2-unit system. If we have, similarly, if we have 3-unit system, the force outage rate remaining the same, what we get? We again get similar thing. 30 megawatt with this probability, 20 megawatt with this probability, 10 megawatt with this probability, and 0 megawatt with this probability. You can see probability, if your load is only 10 megawatt, the probability of getting that 0 megawatt condition, 0 megawatt generation is very low. It's 0.000008. Okay. So I can say this is 8 into 10 to the power minus 6. Yeah. 8 into 10 to the power minus 6. That is a very, very low probability that we will have no generation at all. If our demand is 10 megawatt only, then this system is highly reliable. As I mentioned earlier, whether this level of reliability is good for us or not, that has to be debated upon. We need to find out whether we need this level of reliability or not. There may be certain, cases where we need a very high degree of reliability. In those cases, we may need this much level of reliability also, but not always, not always. That needs to be understood. Expected or mean value, so we need to find out the expected or mean value, which is nothing but this is a long run average value. In long run, what is the average value? That is given by the expected value. So for a random variable x, so Ex is the expected or mean value, is computed as summation of I equals to 1 to n xi pi, where n is the number of outcomes xi, that is x1, x2 up to xn, each with probability pi. Okay, each with probability pi. Now, consider a system with a projected peak load of 10 megawatt. The choices are 10 megawatt units, 5 megawatt units, and 3 and 1/3 megawatt units. Force outage rate of all units is identical and equal to 0.025. So we have a 10 megawatt peak load system, and the choices for us to design the system are, I have 10 megawatt unit, I have 5 megawatt unit, and I have 3.333 megawatt units. Okay, and the force outage rate for all these units are equal and 0.025. Now, what I can do? I can first try with single unit. What is a single unit? I take one 10 megawatt unit. So for me, the outcome can be like this. I have one unit, so that unit can be either in up condition or that unit can be in down condition. So if that unit is in up condition, my load is 10 megawatt peak. This peak is fulfilled and there is no load loss. Load loss is nothing but difference between load power and the available capacity. So available load power is 10 megawatt, available capacity is 10 megawatt. So 10 minus 10 is load loss, that is 0. So expected loss of load is this load loss multiplied by this individual probability, multiply. So load loss is 0. This probability is 0.975. 0 multiplied by this is 0. So there is no expected loss of load, but that single unit can go down also. So 0 unit up means the single unit is down. What is the capacity out? Capacity out is 10 megawatt. So the whole 10 megawatt has been unavailable then. What is the capacity in? Capacity in is 0. We have 0 capacity available now. What is the probability? Probability of this condition arising is 0.025. It is equal to the force outage rate, 0.025. What is the load loss? Sorry, load loss is 10 megawatt. It's written here 0. It's not. It's 10 megawatt. Okay. Load loss is 10 megawatt. So 10 multiplied by 0.025 is the expected loss of load. It is 0.25. See, probability of the load being unserved was 0.025, but the expected loss of load is 0.25 megawatt. Okay, although the whole 10 megawatt has not been served. So this is the expected loss of load. Okay, expected loss of load. So if we have a 110 megawatt unit, the expected loss of load will be 0.25 megawatt. Now consider a 210 megawatt unit case. Again, we carry out the same procedure again, So 2 units up, 1 unit up, 0 unit up, and again you can see this these values. 2 units up, load loss is 0, 1 unit up, load loss is 0, and both units down means we have 0 megawatt available, and the expected loss of load is 0.00625. Okay, this is the expected loss of load, and expected loss of load is this much. Similarly, so this was second case. So this is where we have 100% reserve margin. You can see if we go for percentage reserve margin, peak load is 10 megawatt. We have a 10 megawatt unit, so percentage reserve margin is 100%. So in this case, 2 5 megawatt unit, again you can see here 2 5 megawatt unit. Again, you have both the units available, load loss is 0, only 1 unit available, load loss is this much, both the units unavailable, load loss is this much. Okay, so you can see here, in case of 2 5 megawatt unit, the expected loss of load is same as that of 1 10 megawatt unit case. You can see here, this was expected load loss of 0.25, here also it's 0.25, but loss of load probability there was 0.025. Here loss of load probability is 0.049375. The loss of load probability has increased here. If we are to compare based on expected load loss only, then 1 10 megawatt unit case and 2 5 megawatt unit case for a peak demand of 10 megawatt is same, but not if we also consider loss of load probability. loss of load probability is the sum of the probabilities whereby there is a load loss event. When this loss of load is positive, all these probabilities, they have to be added together. That's what we did here. And similarly, we can see here 3 5 megawatt units. This means the reserve margin will be 50%. So we considered two cases where there is no reserve margin, one case where there is 100% reserve margin, and this case where there is 50% reserve margin. So when the reserve margin is 50%, we can see here 3 units up, capacity out is 0, all the units available, capacity in is 15 megawatt, 3 into 5, probability is 0.975 to the power 3. So this is the probability. Load is 10 megawatt, loss of load is 0. So no loss of load, because loss of load is load minus generation capacity. This is negative. That means we have surplus available. So this has to be positive for loss of load event to occur. So loss of load is 0. Expected loss of load is also 0. In second case, 2 units up, capacity out is 5 megawatt. We still have 10 megawatt available with this probability. So load is 10 megawatt, loss of load is still 0, because load minus capacity available is still 0. So it is 0. So expected loss of load is 0, because expected loss of load is nothing but this is loss of load multiplied by the corresponding probability. And in the third case, only 1 unit available. So 10 megawatt is not available, 5 megawatt is available with this probability. How did you get this probability? This probability is, this second probability is 3p square q. P is the availability, Q is the unavailability. Okay. In this case, this is thrice PQ square. P is the availability, Q is the unavailability. So we get this probability. So now loss of load is 5 megawatt, because we only have 5 megawatt available. 10 minus 5 is 5. So 5 multiplied by this will give this expected loss of load 0.009140625. Okay. And 0 unit available means all the units are outage now. What capacity is outage? 15 megawatt. What is the capacity available? That is 0 megawatt. What is the probability? Probability of this condition occurring is Q to the power 3. Okay, that is 0.025 to the power 3 will be this much. Load is 10 megawatt. Loss of load is 10. 10 minus 0 is 10. And what is the expected loss of load? This multiplied by this. So this point will be shifted to this. Okay, so this is 0.0015625. And loss of load probability is sum of those two probabilities. This probability and this probability where loss of load event has occurred. So all the probabilities where loss of load event occurs, they added together give rise to loss of load probability. This is the probability only. And expected loss of load is nothing but sum of all the expected loss of loads. This and this, putting them together, adding them together, will get 0.009296875. So this is the case when we have a 50% reserve margin. Okay. And then we have a case 4 where we have 4 units of 3.13 megawatt, that is 3.33 megawatt. Why we choose this 3.33 megawatt? Because by choosing 4 units, we'll have a 33.33% reserve margin. So in the first case, we had 100% reserve margin in one case. With 5 megawatt unit, we had 50% reserve margin. And now with 3.33 megawatt unit, we have 33.33% reserve margin. Okay, with those 4 3.33 megawatt units. So when all 4 units are available, total capacity available is 13 and 13. that is 13.33 megawatt. So this is the probability. What is the probability? Then P to the power 4. So that is 0.975 to the power 4 will be this much. And then the load is 10 megawatt. Loss of load is 0. Expected loss of load is 0. 3 units available. 10 megawatt is available with this probability. Load is again 10 megawatt. This minus this is still 0. Loss of load is 0. So expected loss of load is 0. When 2 units available, we have 6 and 2/3 megawatt, that is 6.67 megawatt. Capacity unavailable is also the same, 6.6 2/3 or 6.67 megawatt. And this particular condition occurring has a probability of this much. That is, this is, we have to find out according to the binomial expression. So this should be, I think, 4, this is, I think, yeah, 4 p q to the power 3. Yeah, this is the third case is 6 p square q square. Yeah, and the fourth is 4 p q to the power 3, and this has this much. So the loss of load in the third case is 3.333 megawatt, 10 minus this much, and the expected loss of load is this much. You multiply this by this probability. Okay, and similarly you get corresponding probabilities for 10 megawatt unavailable, only 3.33 megawatt available, and the loss of load of 6.67 megawatt, and expected loss of load of 0.000040625. And when there is none of the units available, capacity out is 13 and 1/3 megawatt, capacity in is 0, and the probability is this much, very low. Load is still 10 megawatt, loss of load is also 10 megawatt, and this is the expected loss of load. This multiplied by this probability is the expected loss of load. So by adding these 3 probabilities, these 3 last probabilities, I will get loss of load probability, because in these 3 conditions we have a load loss event. So loss of load probability and expected loss of load. I add all these 3 loads together, 3 megawatts together, and that will give me total expected loss of load, okay, for the system. And then when we compare them together, you can see case 1 and case 3, we have 0% reserve margin. Expected loss of load in both the cases are same, but the probabilities are different. You can see here, probabilities are different. Whereas in case 2, the reserve margin is 100%. Therefore, you can see loss of load probability is very low, and expected loss of load is also low. In case 4, reserve margin is 50%. So loss of load probability is higher than in case 2, because in case 2 we had 100% reserve margin. Case 4 we have 50% reserve margin. And similarly, the expected loss of load is also higher here compared to the case 2. And in case 5 now, the reserve margin has been further reduced to 33.33%. Loss of load probability is higher than in case 4, and expected loss of load is also higher than in case 4. Okay, so the higher the reserve margin, the lesser will be the loss of load probability and expected loss of load, you know. So it depends only in the percentage reserve. Okay, so expected loss of load depends only on the percentage reserve margin, whereas loss of load probability also depends upon the number of units. You can see for the same percentage reserve, for the same without 0% error margin. Same case in case 1 and case 3. You can see loss of load probability in case 3 is higher than in case 2. Okay, case 1. So when planning, we have to consider these things also. From this perspective, we can say that 110 megawatt unit is better than 25 megawatt unit. Okay, we can say that this is better. But obviously, we have not explored other avenues also. From where we can come into different conclusion that having 25 megawatt unit is better than having 110 megawatt unit. So that needs to be explored further. Now, how to choose the capacity combination? How to choose a particular capacity combination. So one is the percentage reserve criteria. Another is the N-1 criteria, and another is the probabilistic criteria, LOLP or LOLE or EENS or EEV, and also there is another criteria which I did not write here, is known as LOE. Okay, so LOLP stands for loss of load probability, LOLE stands for loss of load expectation, EENS stands for expected energy not served, EUE stands for expected unserved energy. Both are same, expected energy not served or expected unserved energy, and LOE stands for loss of energy expectation. Okay, loss of energy expectation. So each of them, see, each approach gives different result. So which criteria we are following, that may give you different result. And the reliability always comes with cost. So having higher reliability or having lower than required reliability or having higher than required reliability, both conditions are not acceptable or not desirable. Okay, we always try to maintain optimal reliability in the system. Okay, we try to maintain optimal reliability in the system. So not only under reliability, but over reliability is also undesirable. And it is important to assess the reliability of the system and check whether it fulfills the requirement or not. Without being able to assess the reliability, we don't know whether we are having over reliability or over reliable system, or we are having under reliable or unreliable system. Over reliable system will become more expensive because over investment has been made in the system. So customers have to pay more to the electric utility. Under reliable system or unreliable system or under invested system will be more expensive to customer, although the customers have to pay less to the electric utility. They are incurring additional losses. Some losses are directly measurable, some losses are not directly measurable. Okay, these losses have to be considered. If they are considered, then under invested system are also expensive to the customers. They are also undesirable to the customer. Now, to know about the differences for different criteria, let's see. We have a system of 10 generating unit, 4 10 megawatt force outage rate of 0.02, 2 20 megawatt force outage rate of 0.025, and 2 30 megawatt force outage rate of 0.03. The system load is 110 megawatt. So this is the system load. So if we consider, so loss of load probability in this case that we have found is 0.003968 based on N- criteria for the loss of largest unit, that is 30 megawatt unit loss. Because see here, it has been chosen that the load is 110 megawatt, generation is 140 megawatt. So loss of largest unit means 30 megawatt unit will be lost. So this criteria and the system's condition is actually matching. So therefore, from probabilistic point of view also, we find this loss of load probability of this value, and from loss of load probability perspective also, we are getting the same value. And considering a 20% reserve in the system, if we consider 20% reserve in the system, because of the unit combination, this will also give us the same value of the loss of load probability. But see, when we consider three different approaches, one is the percentage reserve margin, another is the loss of largest unit or n-1 criteria, yeah, and another is the probabilistic approach, we will have different results. Here the results are coinciding because I choose a system in such a way that 110 megawatt is the load, 140 megawatt is the available generation. So loss of largest unit is 30 megawatt. So n-1 criteria 30 megawatt, and if I choose 20% reserve margin, then it will be 24 megawatt. So I do not have a 24 megawatt unit. So either I have to choose 30 megawatt or 10 megawatt and 20 megawatt. That is again 30 megawatt. So therefore, again the reserve here has to be 30 megawatt. So loss of load probability came out to be 0.009368 here. So in hierarchical level 1 evaluation, what we do? We have a generation model, we have a load model, and when we put them together, we obtain the risk model. Okay. So from this risk model, we get these risk parameters. Okay. Risk indexes, risk indices we call. Loss of load expectation, loss of energy expectation, frequency and duration, and other indices. Frequency and duration of load curtailment. Frequency and duration of load curtailment. That's why they are risk indexes. And why the load curtailment occurs? Because of insufficiency of the generation to serve the load imposed on the system. So by using this model, we evaluate the risk indices in the power system. So what is the loss of load expectation index? It is the expected number of hours or days in a given period of time that load exceeds the available generation. So how to find whether it is a day or hour? If we are considering hourly load model, then it will be in hours. If we are considering daily load model, means daily peak load model, then it will be in days. Okay. So whether you find it in hours or days depends upon whether you are following a hourly load model or daily peak load model. Okay. And you can see here a two-state model for power system reliability evaluation as HL1, up state and down state. This lambda is called transition rate from up state to down state, and this lambda is also called failure rate or hazard rate. Means with this rate, the unit here will move from up state, operating state to failed state, and mu is called repair rate. Repair rate. From this rate, unit can move from down state to up state, means unit get repaired with this rate. Okay. And A is availability of the unit given by mu divided by lambda plus mu, and U is unavailability, lambda divided by lambda plus mu. And from this expression, we can get this form: downtime, sum of uptime plus sum of downtime. And for A, we can get similar expression: sum of uptime divided by sum of uptime plus sum of downtime. Okay. And there may be many variations and expansion of the presented model, some of which are inclusion of directed states in generating units, as I mentioned earlier. 4-state models are used to recognize the conditional probability of failure associated with peaking units. Also, recognition of non-exponential state residence time distributions and variable transition rates due to component aging, repair, and maintenance practices. So if you consider those things, then these models have to be changed. We have to adopt different models. Means we have a 2-state model here, there might be 3-state model, 4-state model, and theoretically n-state models. So generation model means models associated with the generating unit. You can see a force outage rate of 0.03, 520 megawatt units means 100 megawatt generating station or generating system. And you can see again, you can construct this type of table. This type of table is also known as capacity outage probability table. This is capacity outage probability table. It shows the capacity outage with individual probability. You can see 0 capacity will be outage with this probability. 20 megawatt capacity will be outage with this probability. 40 megawatt will be outage with this probability. 60 with this probability, 80 with this, and 100 with this probability. And sometime in literature, if we are considering only up to 6 digits after decimal, then the last one will be shown as 0 here. The last 2 will be shown as 0. But here I am considering more numbers than 6 digits, so it's not 0. But sometime you can see in the literature and see that these numbers are 0 because we are considering only up to a certain number of digits after the decimal. And the load model is shown like this: peak load of 60 megawatt and load factor of 0.75. So 60 megawatt here and the lowest load will be 30 megawatt. So this gives us the 75% load factor. So if 60 megawatt was present all the time, the load factor would have been 1. Okay, so this would have gone in this way. So this one reduces the consumption by 25%. You can see. So that's why the load factor is 0.75 only. And then risk evaluation. What we do is we put the load model and the generation model together, or we cumulate them together, and then we find out, for example, when capacity outage was 0, whole 100 megawatt is available with this probability, and outage time is 0 hours, LOLE is 0, and loss of energy expectation is also 0. So when 20 megawatt is outage, we still have 80 megawatt available with this probability. Outage time is 0 means all the load will still continue to get supply. So therefore, this outage time means outage time for the loads is 0 hour. All these things are also 0. In the third state, when 40 megawatt was outage, we still have 60 megawatt available. That means with this probability. So our load is also 60 megawatt. So still the load is fulfilled. So no outage occurs. So when the generation available was 40 megawatt only, with this probability, 20 megawatt has been lost here. So for how long? For 5,840 hours. How do we know this? From this graph. Okay. So when 40 megawatt is available, this much, 40 megawatt is available here. So this hour is 5,840 hours. 5,840 hours. Okay. When 40 megawatt is only available. And when 80 megawatt is unavailable or only 20 megawatt is available, so this comes. So this is 30 megawatt. So 20 megawatt. So when 20 megawatt is available, always there will be loss of load. So that is for 8,760 hours. You can see here. When only 20 megawatt is available to us for the whole year, that is 8,760 hours. That is the time under observation. Load will be unavailable. Okay. So loss of load will be this much hours per year, because I have to multiply this by this probability. So this is the expected value. This by this probability, this is the expected value. Okay. So, and this again also by the same way. And this is loss of energy expectation. Again, I have to find the energy. How I'll find the energy? I'll find the energy from here. For this case, 40 megawatt case. So this is 40 megawatt, 5,840 hours. So I'll multiply that 40 by 20 by 5,840. Yeah, I'll get the energy, because that energy cannot be available. So I find that energy here. You can see that energy is multiplied by this probability. So that will give us the loss of energy expectation. Similarly, this and these are also obtained in the similar manner. Although the energy value here and here will be higher, but the probability value are lower. Therefore, loss of energy expectation are lower here. And you can see loss of load expectation is 1.518 hours per year. This is when we used this load model. This is hourly load model. Okay, this is LOE when we used hourly load model. So okay, so we used hourly load model. Therefore, this LOLE value has been in hours per year. If we had used daily load model, then it would have been days per year. So the days per year cannot be converted into hours per year by multiplying the day by 24 hours. No, you can't do that. You have to use hourly load model, then only the result of loss of load expectation will be in hours per year. Okay, in this way. So the loss of load expectation versus peak. So we have a peak of 60 megawatt. So you can see this loss of load expectation. If we change the peak, because we have a peak of 60 megawatt, you can see here. For this 60 megawatt, my loss of load expectation was 1.5 hours per year. Okay. But if I change the peak to 40 megawatt, then it drops below 0.1 hour per year. Okay. 0.1 hour per year. So if I keep on increasing, make it 45, this is the loss of load expectation. This is an exponential. This is an exponential curve. You know, this is an exponential logarithmic value. So therefore, this is not linear. This part is linear. This part is not linear. So you can see for the force outage rate of 0.03, this was the initial. And what will be the impact of changing the force outage rate from 0.03 to 0.05? You can see we increase the force outage rate means there will be more force outages of the generating unit. That means the risk index has to increase, and loss of load expectation is a risk index. Its higher value indicates higher risk. Similarly, loss of energy expectation is also a risk index. Its higher value means higher risk. Okay, so therefore, when this force outage rate of 0.05, loss of load expectation and loss of energy expectation have actually increased. We can see here. So, and what will be the impact of addition of a new unit? Sorry, just a moment. I think, yeah. Yeah, I think we are, I have overhead, yeah. So,
yeah. Let me see, sir. There was some queries in between in the session.
Okay.
So, participant, do you have any query? Please raise your hand. No, I don't think so. नहीं वो हैंड रेज हैंड आता ना sir, I don't think so. Thank you very much then for your session for today. We will continue further tomorrow.
Yeah.
At the same time. Thank you very much, sir.
Okay. Thank you. Thank you. Bye bye.
Thank you. Bye. Bye.
Bye.
कर दिया रिकॉर्डिंग बंद हो गई